Hello everyone, and welcome back. Today we're going to continue our exploration of limits of functions and focus on a few special identities that are actually quite useful and several other topics and applications that we'll discuss later on. So the first limit that I want to consider is the limits as x approaches 0 of the sine function divided by x, or some people refer to as the sinc function not defined at x is equal to 0. And if you don't know what this function sort of looks like, it's sort of like a sine wave that sort of diminishes as x approaches plus or minus infinity. So if you were to analyze the graph of this curve, it's obvious that the function does approach something from the left and from the right, and in particular, this value is equal to 1. But how to prove it? Now, some people will use some tricks from calculus, such as L'Hopital's rule and Taylor series, but you technically are not allowed to use those rules here because those rules and tricks are actually based upon this assumption, which of course turns into a circular logic argument, which is generally not a good thing. So what we want to do for this limit and also all the other special limits that we're going to discuss today is just approach them from just only assumptions, algebra, and geometry principles that we have actually already built before we have encountered those calculus-based tricks, right? So without further ado, let's get started. So we're working with the function sine of x, right? So obviously the unit circle may be our friend here. So what I want to do is I just want to focus on quadrant 1 of the unit circle, and let's assume that we take an arbitrary angle, let's call that angle x, and let's consider the point of intersection with that unit circle, where that point is 1, 0, and this point is 0, 1. And the question that I want to ask here is, what is the area of this triangle here, where this is a right triangle, and I'm going to be calling this area A1. So if that interior angle is angle x, then we know that this point here is going to be cosine of x times the sine of x. So the area of that right triangle is going to be 1/2 the base, so keep in mind cosine is the x, sine is the y, so 1/2 base times height. So we get a1 is equal to 1/2 cosine of x times sine of x. So that's the first area that I want to consider, and we're going to consider a couple other areas as well. So let's consider the same exact circle, although this doesn't look like it's drawn to scale. Let's actually change it a little bit so it looks a little bit more like the circle above it. So again, that's going to be 1, 0. That's going to be 0, 1. We're going to consider the same exact line. Let's assume that angle is x. But now what I want to do is consider this area here, this entire sector. I'm going to call that A2. So remember that the area of an entire circle is pi r squared, and in particular, the unit circle has the area of pi 1 squared, or pi r squared, where r is equal to 1, which is just going to be equal to pi. So that's the area of an entire unit circle. So if I want to find the area of a sector of a circle, in particular A2, I'm going to call this, so A2, this is just going to be equal to a fraction of that entire circle. And since we're measuring a fraction of a circle in terms of the interior degree, where the interior degree is equal to x, and let's assume this is in radians, where the denominator is equal to 2 pi, then the area of that sector is just going to be a fraction of the area of the whole circle, which is going to be pi. So if we cancel out those pi's, notice that we're going to have just 1/2 of x pi, or 1/2 x. And some people may prefer to write that as just x divided by 2, which we're going to write it as. So that's the second area of interest. So let's consider another picture. Same base circle. 1, 0, 0, 1. Same interior angle x. And now let's consider the line tangent to the unit circle at the point 1, 0. And we're going to be focusing on that point of intersection there, which you should know from basic trigonometry is the point 1 tangent of x. So my next question and focus is going to be the area of this circle, which is again going to be a right triangle. So A3 is going to be equal to what? So the length here is going to be 1. The height is going to be equal to tangent. So it's going to be 1/2 base times height. which is going to be 1/2 times 1 times tangent, which is just going to be equal to 1/2 of tangent, which we know to be equal to sine x, all over cosine x, which is pretty much how I'm going to leave it. So I'm just going to write it as sine x, all over 2 times cosine x. So that's my third area. So if you look at all these areas, notice that this pink area is larger than that purple area because we have that outer sort of rounded triangle. And that purple area is greater than that green area there because we have that sector piece on the right hand side sort of taken away from that left hand green rectangle. So we obviously see that for an arbitrary angle x, we have that a1 is less than or equal to a2 is less than or equal to a3. So if we actually write down those formulas that we derived for each of those areas, what will we get? So we're going to have 1/2 sine of x cosine of x is less than or equal to x divided by 2 is less than or equal to sine of x all over 2 cosine of x. So one thing we do know is that the limit as x approaches 0 of cosine x, this is going to be equal to the cosine of 0, which is equal to 1. Right? And also notice that with our inequality, we have a 1/2 everywhere in this expression. The next thing that I want to do is I want to divide both sides by the sine of x. And let's assume that x is slightly greater than 0, because we're approaching 0, so we need to approach it from the right and also the left, but let's approach it from the right hand side. This is an odd function, so it should be approaching the same exact point. So once we divide by sine, then we're going to have cosine of x on the left is less than or equal to x divided by sine of x, and that's going to be less than or equal to 1 divided by cosine of x. And then what I want to do is I want to flip both sides of this inequality. So that's going to give us what? So we're going to have the reciprocal of 1 over cosine, which is going to be cosine, is less than or equal to the reciprocal of the interior, which is sine x over x, less than or equal to the reciprocal of the left, which is going to be 1 over cosine of x. Now, we have that the sine x function is in between the cosine function and the 1 over cosine function, aka the secant function. So if sine x of x is always between these two curves, then the limit also will be in between these two curves as well. Some people refer to this as the squeeze theorem. So we have the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine x over x, which is the limit that we want. And that's less than or equal to the limit as x approaches 0 of 1 over the cosine of x. So keep in mind the limit as x approaches 0 of cosine of x, that's just equal to 1, is less than or equal to our limit, which we don't even know it exists, but from the graph we have evidence to believe that it will. And that's going to be equal to 1 divided by 1, which is obviously equal to 1. So, provided that the limit does exist, and one can provide a formal proof for that, we see that whatever the value is in between 1 and 1 inclusive. Therefore, since there's only one number that satisfies 1 is less than or equal to L is less than or equal to 1, we have that limit is precisely equal to 1. And that provides a geometric proof for this particular limit, which is actually pretty nice. Now one can say, okay, well, what can I use this for in terms of just basic, clever limit problems? So one immediate problem that you can solve is one of the form the limit as x approaches 0 of sine of ax divided by the sine of bx. And let's assume that a and b are real numbers with b not being equal to 0, else you have a non-existent thing. So what is this going to be? So I can actually write this as the limit as x approaches 0 of bx divided by bx times ax divided by ax times the sine of ax over 1 times the sine of 1 over the sine of b of x. So all I've done here is I've just multiplied top and bottom of this expression by a fancy form of 1. Now what I want to do is I want to move this ax under here, and I want to move this bx over here. And what I want to do is I want to redefine these things in a slightly different way, and I'm actually going to put up my ax and bx in the front. So I'm going to have, because those x's do cancel, so I'm just going to be left with a over b times the limit as x approaches 0 of sine of ax all over ax, and then I'm going to use my product rule for limits. The limit as x approaches 0 of bx all over the sine of bx. So notice that if I define u to be equal to ax, as x gets close to 0, u gets close to 0 too. And if I define v to be equal to bx, then as x gets close to 0, v gets close to 0 as well. So therefore, using these substitutions of u and v, I can write this as a divided by b times the limit as u approaches 0 of sine of u over u, and that limit should look familiar. And then we have 1 over the limit as v approaches 0 of sine of v over v, and that limit should look familiar. So we're just left with a over b times, so we know that limit is equal to 1, and we know that that bottom limit is also equal to 1, so we have that limit is equal to just a over b for the general case. So for example, if somebody asks you, what is the limit as x approaches 0 of sine of 7x divided by the sine of 6x, you would just say that it's equal to 7/6 for the reasons provided above. The next limit is going to look similar to the sine x over x limit. Instead of using sine, we're going to be focused on cosine. But keep in mind that cosine of 0 is equal to 1. So if you consider the limit as x approaches 0 of cosine x over x, that's just 1 divided by 0, which is undefined, because cosine of x over x has a vertical asymptote as x equals 0. But if we consider cosine x minus 1 over x, then we have 1 minus 1 on top, which is 0 over 0. So we have the 0 over 0, which we have referred to as an indeterminate form before. So if it's 0 over 0, it could not exist, or it could exist. So you probably would resort to a graph and realize that this limit actually is going to be equal to 0. But how to prove? So the first thing that I'm going to do is first off start off by writing my limit. So cosine of x minus 1 over x. And similar to some square root problems, notice that on the top I have something minus 1. So what I'm going to do is I'm going to multiply this by something plus 1, top and bottom. And you actually see some magic happen here. So obviously the top we're going to be foiling here. So that's going to be equal to the limit as x approaches 0 of cosine x times cosine x, that's cosine squared x, and then cosine x times 1, which is cosine, and then minus 1 times cosine, which is minus cosine, and then we're going to have minus 1, and then on the bottom we're just going to be left with x times the cosine of x plus 1. So notice here we have these cosine of x's that cancel, which is actually pretty nice. And then we're going to be left with just the limit as x approaches 0 of cosine squared x minus 1 all over x times cosine of x plus 1. Right, so that's pretty nice. So keep in mind this cosine squared x minus 1 can be rewritten because if you remember from basic trig, 1 plus or sine squared of x plus cosine of squared x is equal to 1. So if I do cosine squared x minus 1 on both sides and minus sine squared on both sides, notice that I get cosine squared x minus 1 is equal to minus sine squared x. So if I use that identity here, that's going to be equal to the limit as x approaches 0 of minus 1 times sine squared x all over x times the cosine of x plus 1 in parentheses. Now I'm going to break this limit up into a bunch of little pieces. So what I'm going to do is I'm going to write this as, let's do minus 1 times, let's do the limit as x approaches 0. Let's do sine x over x as the first term. And then for the other sine x, let's just do sine of x all over cosine of x plus 1. Right? So notice that we have minus 1 here. And then times this limit we've already proven, that's just equal to 1. And over here we have what? So sine of 0 is going to be equal to 0. Cosine of 0 is going to be equal to 1, and 1 plus 1 is going to be 2. So we have negative 1 times 0 over 2, which is 0. That's equal to 0, which is what we aim to prove. The next limit is quite interesting and actually quite nice. So we have the limit as x approaches 0 of the natural log of x plus 1 over x. So if you try to substitute 0 in for this, we get the natural log of 1 over 0, which is just 0 over 0, which is again indeterminate form. So one could ask, well, it could not exist, it could be equal to 1, it could be equal to 0, it could be equal to 10, we don't know. But if we look at the graph of this function, natural log of x plus 1 over x, we will actually see that this function is getting close to 1. But again, how to prove it? So what I'm going to do is I'm going to approach this from the inverse perspective. So I'm going, instead of looking or trying to show that the limit as x approaches 0 of this function is equal to 1, I'm going to approach x is equal to 1 for the inverse and show that that limit is equal to 0. And that's going to imply this particular result. So my relation that I'm interested here is the natural log of x plus 1 all over x. And now what we want to do is we want to find the inverse of this relation. So to find the inverse of this relation, we're just going to switch x and y. So x is going to be equal to the natural log of y plus 1 all divided by y. And we can multiply both sides by y here, so we're going to have xy is equal to the natural log of y plus 1. And then we can exponentiate both sides by e, so we have e to the power of xy is equal to y plus 1. And then we're going to have this is equal to e to the xy minus y is equal to 1. Now, if you have followed me in the past where we introduced the Lambert-W relation, we already found that the solution to this equation is in terms of the Lambert-W relation. So this is actually just equal to minus 1 over x times the Lambert-W relation evaluated at minus x e to the minus x plus x. Right? So now we have this particular relation of interest, right? And in case you don't remember what the Lambert-W relation is, or maybe you never learned it, let me just give you a quick introduction. So the Lambert-W relation has this interesting property. So it's multi-valued on the left-hand side of the y-axis, and this point right here is minus 1 over e, and it has that sort of inverted local maximum at the point negative 1, and this is what we refer to as the Lambert-W relation. Right? So what I want to do is I want to take the limit as x approaches 1 of this function. So the limit as x approaches 1 of this function is going to be equal to what? So this is going to be equal to w of minus x e to the x plus x all divided by x. But notice the issue with this function is that x is equal to 0, not 1. So we can actually just plug in x is equal to 1 into this relation and get some answer out. So we're going to have the Lambert-W relation evaluated at minus 1 times e to the minus 1 plus 1 all divided by 1, which is just going to be equal to the Lambert-W relation of negative 1 over e plus 1. And we already know that the omega relation at negative 1 over e, that's just going to be equal to minus 1, regardless of the branch that you choose. So we have minus 1 plus 1 is equal to 0. So, since this is the inverse relation of the relation that we want, therefore we have as a result, by reversing our domain and range, that the limit as x approaches 0 of the natural log of x plus 1 over x is actually precisely equal to 1. And that's the result that we aim to prove. The next special limit that I want to look at and prove is this following limit that says as x gets close to plus or minus infinity, the expression 1 plus 1 over x all raised to the x gets closer to the natural logarithm base e, which is approximately 2.71828. So this limit is the one we aim to show, in particular the limit as x approaches plus or minus infinity of 1 plus 1 over x to the x. How are we going to show that this is indeed equal to e? So the first thing I'm going to introduce is the basic properties of the exponential and logarithm, which are actually easily provable without any of these rules for which we're using here, which we'll talk about later. So I can write this as the limit as x approaches plus or minus infinity of e to the natural log of 1 plus 1 over x to the power of x, because e and natural log cancel, So once they cancel, we're just left with the original. So we're technically working backwards, but this trick is actually very, very useful and will be used in some technical derivative tricks a little bit later on. Now, my focus is going to be this natural log expression. Here, this is the exponent of the argument of natural log. Therefore, I'm just going to drop that into the front. Once I do so, notice that e does not have any x's in it, so I can pass my limit into that exponent. So once I have that, this is going to be equal to e to the limit as x approaches plus or minus infinity of x times the natural log of 1 plus 1 over x. So that's my expression there. Now, what I want to do is I want to perform a little substitution here. So I want to introduce the function 1 over x, which we should know to be equal to this curve. So let y be equal to 1 over x. So notice that as x gets close to plus or minus infinity, y gets closer and closer to 0. So what I want to do is I want to rewrite this expression such that I have 1 over x there and a 1 over x somewhere else. So I'm going to have the limit as x approaches plus or minus infinity of the natural log of 1 plus 1 over x, all divided by 1 over x. I'm reciprocating that linear term x that's in the front. So now I'm going to change this into terms of y and change my limit value. So this is going to be equal to e to the limit as y approaches 0 of the natural log of 1 plus y divided by y. As already discussed, this is one of the special limits that we just proved. We already know that that limit is equal to 1, so this is just equal to e to the power of 1, which is equal to e, which is the limit value that we sought out to prove. So the limit as x approaches plus or minus infinity of 1 plus 1 over x is just equal to e. Using some other use substitution tricks, as we have shown here, you can actually prove a more useful result. In particular, the limit as x approaches plus or minus infinity of 1 plus c divided by x to the power of x. This is actually equal to e to the power of c, where c is a real number. I invite you to try and prove that on your own. But those are some of the very important limits. Some people call them special limits, some people just memorize them. But those are the proofs that are sort of underline why they actually are what they are. And these proofs are independent of any calculus tricks that you need later on, which are technically not really valid proofs. So I hope you enjoyed this video, and I'll see you in the next one. Take care.